If I ever went back, that's what I would do.
You're right, though.
Yeah. It's like, I love history. All right. Last thing. You have successfully survived Calc 2 to make it to the end.
Yeah, I'm just saying, like,
Well, I guess everybody has a different definition of success. Like, so, pretty much everybody is passing. Nobody's in that major, like, crazy danger zone. So, which I'm going to count that as a success. So, I was telling Scott, I was like, I was waiting for the second one because you never know. It's like, as I was going through and looking at the tests and stuff, I realized that this is the first Calc 2 class that I've taught in person since COVID hit. So, because I only did in the springs, 2020 was the year we left. 2021 and 22 is both Elron classes. So, and I've noticed, so it's like I've been using a variation of the test that I used back in 2019 and 2018 and stuff like that, because they basically the same things I've taught. And it's like I've noticed that there's a distinct difference in the classes, this class compared to what I had pre-COVID. And it's not necessarily like an ability level, but it's definitely a speed level, like a processing level. You guys are taking a lot more time to process things, which could be good and bad. So it's like, that's why I noticed the first couple tests that you guys had, it's like it took you longer than I was ever expecting you to take on the tests. So that's why the last test we did online or at home, so it made it a little bit easier for you. The next test is actually a little shorter, so that should make it a little bit easier for you. And I've redone the final, so that should be a little bit easier for you to complete in the class period. So the practice test for chapter 10 and 12 is already up online. It's in the post. I'll just update it with the class notes and the video from tonight. So that's already up there, so you can look at it and practice it. We'll go over that on Tuesday. You are still allowed your index card for the tests. My goal is to have the practice test for the final up there on Tuesday. So you'll be able to get that and start working on that. And then the next Tuesday after that, we'll do the review for the final. And then your final exam is on May 11th. You are allowed one sheet of paper for the final exam. If you would like to use your 4 index cards, you're more than welcome to use your 4 index cards if you kept them. That's why I do a sheet, because it's basically the same as your 4 index cards. So either way works for me. So you're allowed one sheet of paper, both sides, or your 4 index cards for the actual final exam. The next 2 Thursdays, I'll be in the room by 4 o'clock. So if you want to come early, you're more than welcome to come early, get your test done, and get out of here. At least that's the hope, that you can get your test done and get out of here before 6:45, 7 o'clock. If I've done what I said I did earlier this talking, you should be able to. So, any questions with how the next 2 weeks are going to go? I have not heard anything about evaluations. I know I heard something at the beginning of the semester that they might be looking to do them online, but I haven't heard anything about evaluations. So we still got a couple more weeks left of class. So if I hear anything, I'll let you know. They might be just doing them online and sending you guys emails. That is extremely possible. So, yeah, I know my other class was asking, so that's why it's like I brought it up. So, it's like I doubt they're just going to put it, like they might put it in Blackboard, but they'll have to send out some kind of email, because I know not everybody uses Blackboard. So, although I might be forced to go that way with some other classes for next semester. I'm not happy about that. All right, let's look at the last part of vectors that we're going to look at, which is the cross products. So we focused on Tuesday about the dot product, and I said there's 2 different ways that we can multiply vectors. So the dot product, we just multiplied and got a single value out. You can do that with two-dimensional vectors or three-dimensional vectors. The cross product can only be done with three-dimensional vectors. Okay. What the cross product is trying to do is it's actually trying to find a orthogonal vector to those two vectors. So it's a vector that it would cross both of them perpendicular. This is why it has to be in 3 dimensions. Okay. Because if I had 2 lines on a two-dimensional surface, the only way that I could have one line cross them at 90 degrees would be if they were parallel. If they were anything other than parallel, I could not have them both cross at 90 degrees. So, but in 3 dimensions, we can. So the cross product is set up by this equation here. So it's the AB. Can you see that? Oh, I can make it a little bigger. So you can do this one of 2 ways. Make the equation a little bigger so you can actually see the equation better. So when was the last time anybody here saw matrices? I know I haven't done matrices in here. That's what I was just asking. Okay. So these right here, that's a matrix. Okay. And the 2 lines on the outside mean it's the discriminant of that matrices. So it's going to give you a single number. Basically, what that is, you're just going to cross them and subtract the values. So this would be A2 times B3 minus A3 times B2, which, if you notice, is exactly that there. Okay. So it's just a simpler way to write that if you remember what the discriminants are. Okay. We're going to look at some other things a little bit later that you're going to have to look at the matrices for. So understanding them both is very helpful. So, but all we're looking at is that discriminant. So we're basically just going to cross multiply and subtract the values is in essence what you're doing. Okay. And the same thing with the second one. So we would do this. So it's that I and then minus A1 B3 minus A3 B1, and then that would be J, and so on and so forth. So it's basically those values there. All right, so I would write down both of them in your notes because they both do have their use cases, although they're going to give you the exact same answer. The other thing that I want you to notice about this is the cross product is a vector. It is not a single value. Okay, so the first one you see it's the first value comma, the second value comma, the third value. And the second one that shows you it's the IJK. Okay. So the cross product is a vector, not a single value. Remember, the dot product, we got a single number. So this is creating a vector that is orthogonal or perpendicular to multiple vectors. Okay. So let's find the cross product of these two. All right, so I'm going to actually go through and show it to you with the matrices so you understand how to use them. This is also the way the book does it as well. It actually is easier to put the things together, and when we start dealing with the triple products and stuff before the end of the class, knowing how to use the matrices is very helpful. So the cross product of A and B, we're going to have this one. Let's use it. So we have that. I, J, okay. So you put the 3 letters at the top, and then we put the numbers underneath them. So I, J, and K go at the top, and then 1, 3, 4, and 2, 7, -5. Now, when you're setting up your discriminants for this, basically to find, so for I, I'm going to cross out that row. I'm going to take the other numbers. So it's 3, 4, and 7, -5. I. I'm going to write this, and then I'm going to do the next part. Then I eliminate that row, or sorry, that column, and I use the other numbers on either side of it. Okay, so wherever the letter is, that's the one I'm eliminating. Okay, so when I use the I eliminated the first column, and I just took the other two columns, and ignore the top. I take the second one, I'm crossing off that middle one, that J, and I have the 1, 2, and the 4, -5. And then it's plus, and then I do the same thing for the K. So 7, K. So I'm crossing out that column. So I end up just keeping those 4. And it's plus, minus, plus.
Can it always do that?
Yes. Okay. All right. So now we got to find our discriminant. So cross multiply and subtract. So 3 times -5 is -15. Minus 4 times 7 is 28. So this becomes -43i. Cross multiply. So we have minus -5 minus 8. So -5 minus 8 is -13. The minus sign out front. So it's positive 13. Okay. And then this one, cross multiply. So I have 1 times 7 is 7 minus 6. So that is plus 1. Okay. So this one is -43i, 13j plus k. I'm actually going to have you guys try one more of these. Let me grab one more. Just because I'm not quite, I want to make sure you guys have a little bit of practice with the matrices before we start using them. This one. All right. Find me this one. Try this one. Write it down, and then I'll go back to the previous page so you can make sure that you're doing the steps right. Because everything after this kind of is using the cross product. So I want to make sure you guys can at least figure that part out first. Huh? Okay. There you go. Are they in the ComNet? My ComNet? Or
no, it's through, go into, self banner.
yeah, the banner site. Yeah.
Things like value valuations.
Got it. Okay. All right. I will. Remember, fill it out before I turn in your. No, I'm just kidding. Gotcha. So it's under. So you go into banner. I'm just because I'm going to put it on my site so everybody can find it. And it's under registration and schedule, right? Yeah. Okay. All right. Then I can use this. I actually went to Capital at one point way back when, so I actually still have my Capital thing on here, so I can go into it, even though it doesn't work and I can't click on anything. I can use it to. Yeah, I can use it to copy and paste things. All right, good. Oh, I was going to go back to that slide. Actually, no, let's do it. So A cross B. Okay. So those should be that should be your matrix that you're looking at. So there's no I, so I have a 0 there. That's better. So I have the 2 minus a negative 12, which is 14. 0 minus a 4. And then I got to change that sign because there was a minus sign in front of it, so that's plus 4. And then 0 minus a negative 2, which is plus 2. It's all sign errors.
Yeah.
So, all right, let's start using it. So, I already talked briefly about that the vectors the cross vector is orthogonal to both A and B. That means that they meet at 90 degrees, they're perpendicular to it. So we can use, if I do the cross product with the dot product of A, remember the dot product, if it comes out to be 0, that means they meet at 90 degrees, correct? So this just here is the proof of that they're orthogonal. And you can do the same thing for B if you change to B there. So if you take the dot product of the orthogonal with any one of the vectors in it, it should come out to be 0. That's the entire purpose of it. Because they're orthogonal, I can actually start to use this to come up with some very cool pieces of information. Remember, we're dealing, like, when we're looking at 2 dimensions, things are pretty simple to find. But when we start to look at 3 dimensions, things become a lot more complicated to find, distances and such like that. So the cross products and vector analysis really helps us to come up with some of those options. So the first thing is, remember that we had the dot product helps me come up with my angle. So I'm not going to go through and prove these. So you're going to take it on faith. If you want, the book actually proves it out. So the angle between A and B, we can use the length of A, or the magnitude of vector A, times the magnitude of vector B, times the sine of the angle that's between them to figure out it'll be the same as the magnitude of the cross product. So actually, what was that a minute? So it's just another way to find, it's going to find the magnitude of the cross product, not the actual cross product. It's going to help us do some basic calculations with it in a little bit. The other thing that it works out to is because that's true, if the cross product is 0, the only way that the cross product can be 0 is if the 2 vectors are parallel to each other. Okay? So if the 2 vectors are parallel to each other, the cross product would be 0. Why? Yeah. So why is the angle between them going to be 0? Because if they're parallel, that doesn't mean the angle between them is 0. Right. Remember, a vector, so when we're looking at parallel lines, typically we're looking at lines that don't cross, right? But when we're dealing with vectors, I can move the vector, correct? So technically, 2 parallel vectors are literally the same line. One might be longer than the other one, but they're on top of each other. So that's why your angle is 0. Okay? Does that make sense? Because remember, because every vector I can move to start at the origin. So if I had two vectors, one was here and one was here, right? If I moved those vectors to the origin, they're literally going to be on top of each other because I'm moving them both to the origin. Because remember a couple classes ago, we were looking at the vectors all over the place. They were the same because I moved them. We would subtract the endpoints, and I can get that origin vector that starts at the origin and goes out. So there's no such thing as parallel vectors. They're in essence the exact same vector. One might, the only difference is they might be longer, but they're still lying on top of each other. Okay. So that's why the angle between them would be 0 because there is no angle between them. So that's why that works. So if I do get a cross product of 0, I know they're parallel to each other. All right. So that's helpful because in the last one we were able to figure out perpendicular ones, and this one we're able to figure out parallel ones. All right. So let's find this. So I want to find a vector that is perpendicular to the plane. So remember back to your geometry class. That was probably ages ago. How many points do I need to draw a line? 2. How many points do I need to draw a plane? What's the minimum number of points I need to draw a plane? 3. As long as they are not what? On the same line. All right. So if you think about it, a stool, you can take any stool as long as it has 3 legs, it'll stand. All right. Because those legs will always sit flat on the floor. Okay, even if they're different lengths, they will always sit flat on the floor because that's the way a plane's made. So as long as I have 3 points, I have a plane. So I want to find a vector that is perpendicular to this plane. Okay, that's made by these 3 points. So it's the first. Now we don't have the cross product needs what? It needs it doesn't need 3 dimensions, but it also needs vectors, not points. So I need 2 vectors. So let's find a vector for this one is PQ and PR. So we'll call that A, and we'll call that B. So vector PQ is negative 3i, negative j, a positive j, and negative 7k. So how'd you do? Huh? It was so I have negative 2 minus 1 is negative 3, 5 minus 4 is 1, and negative 1 minus 6 is negative 7. No, positive j. It's 5 minus 4 because we're going Q to P. Q is the endpoint. If we did the other way, they would all have switched. I literally had your thought in the back of my head when I was doing it. I'm like, wait, nope, it's the opposite direction. The points are there because you caught me on that one last time. All right, so now we do P to R. So 1 minus 1 is 0. So I don't need to, I'll put the 0 there just so I have it. We have negative 1 minus 4 is negative 5j. And 1 minus 6 is negative 5k. So now we can do our cross product. So if we set up our matrices for this, I, J, K, -3, 1, -7, 0, -5, -5. So we have A cross B is a -7, -5, -5, I minus J plus K. So we've got, if I don't write these, I'm going to mess up signs. So -40I so 8, -8J. Oh, shoot, 0, not 1. J. $15K. All right, so that vector is perpendicular to the plane that has those 3 points. Okay. So when we were doing these vectors, again, we're bringing them back down. When we did the vectors out, we're bringing them back down to the origin. So the vector that I have is going to go from the origin to that point. So we're not really talking about like, okay, it intersects at a specific point on this plane. We just know that it's orthogonal to the plane, that it's perpendicular to the plane. And also, technically, when we're looking at the perpendicular vector, the length doesn't matter. So if I made this a unit vector, that's fine too. Right? The length's actually going to matter in some other stuff we're going to do in a minute, but just being perpendicular, the length doesn't make a difference. So if I found the magnitude and divided it all, I could get the unit vector, and it still would be perpendicular to that plane. So again, now thinking back to your geometry classes, because that's where a lot of this is going. Where was the situation where you always wanted something that was perpendicular? What did perpendicular help you find? Triangles, because we needed to find what in the triangle. So like the base and the height had to meet at 90 degrees, right? To find the area. Same thing with parallelograms and stuff like that. Whatever you're doing at the base and the height had to meet at 90 degrees, had to be perpendicular to each other. So by having something that's perpendicular, now we can start to take our areas off of the just typical plane and moving it into 3 dimensions to find areas and volumes of shapes that are not flat and not easy necessarily to find. Have those 3 dimensions or on a plane that is not the X plane or the Y plane. So if we look at this, this is a parallelogram, correct? So remember, my vectors can go anywhere. So that's B. That's also vector B, right? That's A. That's also vector A. So it doesn't make a difference where they are. So I have made a parallelogram out of this. If I wanted to find the 90-degree line for this, that's that line right there. Now, if this is on a flat surface, and I knew this angle, which depending on when you took geometry, you might not have known that angle, or you might have, depending on if you had some trig before you did it. So if that right there, and I'm looking at a right triangle, this is adjacent, that's opposite, and that's hypotenuse, correct? Remember that from your trig? Simple right angle trig. So that angle right there, so the sine of theta is opposite over hypotenuse, correct? I know my hypotenuse is B. So I can change that to B. So my opposite is going to be B times sine theta. That's going to be my opposite, or my height. What's the base of this perpendicular or parallelogram? A, right? So it's the magnitude of A. So when we're looking at area, I have base times height. My base is the magnitude of A. My height is the magnitude of B times sine theta, which is that, which we already looked at was the magnitude of the cross product. So if I find the magnitude of the cross products, I now have the area of that parallelogram. Okay. How do I find the area of a triangle if I know the area of a parallelogram? It's half, right? All a triangle is 1/2 base times height, because you just cut it in half. So to find the area of a triangle, I would take the magnitude of A times the magnitude of B times sine theta and divide by 2. So that's a triangle. And then that's the parallelogram in a 3-dimensional plane. Now, in some situations, you will have the magnitude of A and B, and you won't have to find them. If you have the magnitude of A and B, it comes out the exact same way. It's no different. Like if I told you 2 sides of the parallelogram, you can still do this problem. The one piece that you need to know, though, is you need to know the angle. All right. So if we don't have the angle, all I need to find is my cross product, and I can do it that way. So these 3 points should look very familiar. They were the ones we just did. So if I want to find the area of a triangle with these three vertices, we just did those 3 points. We have our cross product, correct? So I can take that cross product now and find the magnitude of it. How do I find the magnitude of a vector? Yep, so I square everything and take the square root of it, right? So negative 40 squared plus negative 15 squared plus 15 squared. I don't know. Let's see. Yeah, it won't give you the exact value. If you do it out, you get 5 over the 5 square root of 82. If you do it on the Desmos, you get 42.277. Is that the area of the triangle? No, that is the area of the parallelogram. So what do I have to do? Divide by 2. So I get 5 halves square root of 82, which is approximately, divided by 2, 22.638. Sure. Oh, thank you. I'll get it before I get up. Huh? Did I screw that? Hold on. Oh, you know what? It's 45. It's 45. Now it's better. I switched screens and I copied the number wrong. Here, if you don't believe me. There. There. That's all right. So that's area of a triangle in 3 dimensions. All right. Here is some properties of cross products. They are a little different than the dot product ones. So for example, if you look at the first one, the cross product of A and B is not the same as the cross product of B and A. It's a cross product of negative B time or of N A. If you have a constant times one of the, or a scalar times one of the vectors, you can look for the cross product and then multiply that by the scalar. The next two just work like distribution. So those work out fine. 5, the dot product of A times cross product of B and C is the same as the cross product of A and B times, or dot times, or the dot product of the cross product of A, B, and C. And then 6, if you have multiple a cross product of a cross product, like we do there, it's not just distribution of cross products. So you'll notice it actually comes out to be a with a couple dot products. I am not going to go through and prove all these out. We are going to actually look at 5 because that's actually going to lead us into the next thing. But I'm not going to prove out 6. So just keep these in mind if you're trying to change things around. It's not purely like the dot product one. It was very similar to what we normally do with multiplication. All right. So let me know when you're done writing. You good? Good. All right. So here is the property 5. So we're going to look at this one because we're going to actually use this one. So what I really want you to look at is that first one. So when we were doing the cross product, we were looking at those three basically were the I, the J, and the K. So when we're doing a dot product times the cross product, we're going to get in essence, a single value out at the end. Because there's no I, J, and K. It's a dot product. We're going to get a single value. So when we're looking at, on the next slide, we're going to start looking at how we look at the matrix of it. These are going to replace the I, the J, and the K. The other thing to notice is that it's always plus. Because in essence, it's a dot product now, not the cross product. The cross products you've dealt with itself. So if you look at it, they basically multiply them out. So they distribute the A1, the A2, and the A3, and then they're factoring out the C1, the C2, and the C3. So they're just showing that it can change. And you actually can do the exact same thing and factor out the B. So the dot product of A times B cross C is actually the same as A cross B times C, or A cross C dot B. They're all going to work out the same way. So I don't know which one you wanted to pull out. The reason I showed it to you is not necessarily because I was worried about that proof and I was worried that you weren't going to believe me. It's because when we go into what's known as a triple product, which is also using cross products, we have the change in our matrices. So you'll notice that the change is at the top. We no longer have the I, the J, and the K. We have A1, A2, and A3. Okay. It's called a triple product. It's actually we're still doing the cross product because that's that there, but it's actually a cross product with a dot product. So we're doing a combination of both of them. That's why they call it a triple product. There's still vectors. Yep, those are all still vectors. That's vector A, vector B, and vector C. So, and based on what we were looking at with property 5, it doesn't really matter the order those are in. Okay, so it doesn't make a difference which order you put them in. This is still going to work. All right. So when we set this up, we're going to set this up the exact same way. So we're going to set it up as A1 times. It's B2, B3, C2, C3. minus A2, B1, B3, C1, C3, plus A3, B1, B2, C1, C3. You notice it's set up the exact same way they were doing the I, the J, and the K. The only difference is there isn't an I, a J, a K. It's the A1, the A2, and the A3. Okay. It's still A1 minus A2 plus A3. This one? Oh, yeah, it's C2. All right. You good, Scott? Okay. All right. I'm not expecting you to remember the name of this. No. It's okay.
Minus for all the plus.
It's A1, 8 minus the middle one plus the last one. The minus is in the middle.
That has nothing to do with the cross product.
That actually is because, so if we go back and look, see how it's always the plus, the minus, the plus. All set. Okay. That's it. All right. This is known as a parallel piping. It's a three-dimensional parallelogram. Okay. So if I was to look for the volume of this, okay, if we're looking for the volume of any three-dimensional shape, how do I find the volume of a three-dimensional shape? We look for the area of the base times the height, right? So we know the area of the base of this because we just did it. The area of the base is the cross product, the magnitude of the cross product, right? That's going to give me the area of the base times whatever the height is. So in this case, when they're doing the calculations for this, the height is the magnitude of A times the cosine of theta. So, and if you look at it, that's because that's the hypotenuse, that's the adjacent. So that's why it's cosine and not sine like we did in the last one. So we have our area and we have our height. On Tuesday, we looked at this. We said the dot product of A and B is the magnitude of A times the magnitude of B times cosine of theta. Now, one little thing here. That's not the magnitude of cosine. Okay? Because you can't have magnitude of cosine. That's the absolute value of cosine. Because cosine can go negative. And when we're talking about three dimensions, we're not talking about just 90 degrees. You can't go past that. So that's the absolute value of cosine. That's why those lines are there. So if you notice, they're not in this one because we weren't dealing with that the last time. So, but if you look at this right here and this, it's very similar. So that's the A, that's the cosine of theta, and then that right there would be B. So if we just replace that with B, I have the dot product of A and B cross product of B and C. So And that right there is what we just found a second ago, is my triple product. So the triple product will give you the volume of a parallelepiped. Yeah. Here, because I'm never going to end up filling it correctly. So, not going to let me copy the one word. Fine. Sometimes this book lets you copy things out of it. Sometimes it doesn't. So I have to choose. There you go. I was going to miss at least one letter in that thing. I was trying to write it out. Too many E's and too many P's and L's. All right, parallelepiped. Okay. So we now can find the volume of a three-dimensional parallelogram. It's great. Probably not as useful as we'd want. What was one of the things that we did with the dot products, though? We were able to take and use the dot products to find if points were coplanar, right? Or it wasn't points. It was hold on. We're able to use the dot products to find things on the plane. If these three vectors are all on the same plane, what's going to be the volume of this shape? Right, because there's no depth, right? So if I find that, if I use the triple product, and it comes out to be 0, I now have shown that those three vectors are coplanar. Right? Which would be helpful. Because one of the hardest things to do is look at 3 dimensions and figure out if things are coplanar or not. All right, because they're going in a bunch of different directions. And unless it's flat, like the x-plane or the y-plane, those are easy. But when we're going in, when we're like shifting the plane, being able to find if things are coplanar are a lot more difficult. So if I find the triple product of those three vectors, they're coplanar, then, and it comes out to be 0, then they're coplanar. I don't have to worry about trying to visualize it. So let's use that to find that these three vectors, to try to show that these three vectors are coplanar.
So I mean, all three occupy only one plane.
Yes. Yep. So that I'd be able to take one sheet of paper and they'd cover all three planes, all three lines, or all three vectors. So the nice thing is, remember what I said, order doesn't really truly matter when I'm setting this up. So when we set up my breakdown, I'm just going to put Now, I want you to, because this is actually kind of finish writing it down, then I'll show you. That's a matrix, simple matrix. We're looking for the determinant of that matrix. Yes, we're using it to find what's known as a triple product, which is a dot product of a cross product. However, it is just a determinant. So if you have a calculator that can do the determinant of a matrix, it's going to give you the exact same answer. All right? That is a simple matrix that you're looking for the determinant of. So if you ever have to do matrices and we're looking for determinants, it's the same thing. There's no difference in it. Okay? And this one does come out to be 0. And if you look right here, that right there is the step we're doing. Okay, it's the first one times that product there. It's the next one times those two. So it's doing the exact same thing that we're doing to look for triple products and for vectors as you would do it if you're looking for a determinant of a matrix. Okay, no difference in the response, the aspect of it. So it's not like we're using this symbol and looking for its special and saying, well, it's kind of like a matrix. No, this is a matrix. Okay, so if we're going through and doing this, I'll write it out now just so you can see it, but it's 1 times -1 or -9, 18, minus 4 times 2, 0, 4, 18. I'll actually do that so you can see the signs. 2, 0, -1, -9. And this comes out to be 0. So that means that these 3 vectors are coplanar. So not only can we use cross products to do area of triangles and parallelograms, those things, we can use it to find volume of 3-dimensional parallelograms and in essence 3-dimensional triangular pyramids, because we can cut that in half. We also can use it to find out if vectors are coplanar or not. We also can use it to find some other information. One other thing that we can use it to find is we can find the distance from a point to a line. Again, something that is very simple in 2 dimensions. When we're looking at expanding that to 3 dimensions, it becomes a lot more complicated. But the process is basically the same. So if we're looking for a point and its distance to a line, this is what we're doing. We have 2 vectors. So my first vector is, in this case, QR. That's going to be my base. My other vector is going to be QP. Remember, it's going to tell me the a line that is orthogonal to both of them. So it's taking that point and basically drawing a perpendicular line. So it's going to give me, when I find the length of that, it's going to give me that distance. So let's find our 2 vectors. So QR is, so we're going to call that A. -1. 4 minus 6 is -2. 7 minus 8 is -1. And then QP, 1. 1 minus 6 is -5. 1 minus 8 is -7. So to do the distance from a point to a line, I need two things. I need the cross product of them, and I'm dividing it by the magnitude of it. So I need the cross product, the magnitude of that, divided by the magnitude of A. So find me the cross product of A and B to start with. Which you should have gotten for the cross product of A and B. It's fine if you did it in the I, J, and K. It's not a big deal. It's no different. You should add 9A minus 8J plus 7K. You did it in the I, J, K. So now we need the magnitude of that and the magnitude of A. So the magnitude of that is square root of 194. And the magnitude of A is 6. So if you simplify this down, you get 97 of the 3. Yeah. The what? The dot product or the cross product? Yeah. So I did another street. So we've got A equals B equals. So if you set this up, I, J, K, -1, -2, -1, 1, -5, -7. So we have -2, -1 over -5, -7, I minus 1, -1, -7, J plus -1, -2, 1, -5, K. Plus multiply, so we got 14 minus 5, so that's 9I. We got 7 minus a negative 1, which is negative 8J. And then we got 5 minus negative 2, which is 7K, which should be what I have. That's fine. So I just wanted to make sure I got this and that right. Gotcha. Yeah, it's all honestly with this, it's gonna be the little signs because it's subtraction, and it always messes things up. Like that's why when I do the subtraction ones, you'll see me write with the parenthesis in there, so I don't miss that negative sign, because it's really easy to miss those. All right, so once we found those, just did the magnitude of each one, and that's the distance. So the distance from this point to that line is that. So with cross products and magnitudes, we can find distances between points in 3 dimensions. We actually can do the exact same thing with a plane. Which one? This one? This one? Okay, that's it. So you can finish writing out time. Just by the same thing by doing a distance from a point to a line, we can do the distance from a point to a plane. Remember, the planes are in 3 points though, so we'll have a couple extra vectors there to deal with. So the formula becomes a little more complicated, but the concept is the same. I'm not actually going to go through and do this one because I want to get into torque and we're running close on time, but I do want to show you the formula for it. So this is the formula for finding a distance from a point to a plane. So, because as crazy as it sounds, like most of the stuff that we do in real life does not work on a plane, like a 2-dimensional surface. Pretty much everything we do is in 3 dimensions. So, and not everything is easily transitive from 2 dimensions to 3 dimensions, all right? Especially if it's not a simple situation. So these formulas, again, a lot of times you're going to use a computer to do the calculations and stuff out, but these are where these formulas came from. And it's all based on that concept of those triple products and the vectors there. So this is where cross products, while being a lot more complicated than dot products are, they're a lot more useful in those situations. And you'll see them more often. So that's the formula from a point to a plane. All right, the last application we want to look at is torque. So, hold on, I'll go back. People are still writing. Another physics concept. So torque is actually the cross product of the force acting on a rigid body by the position vector of r. So you also can look at it as the radius. That's because most torque is going to be in a circular fashion. So r is your radius, but it's that vector of that radius. So the length of it actually does matter. And then the force acting on it in a specific angle will give you your torque. So this is the formula we're going to use to find torque, because we want a specific number, not a vector, which is what that would give us. So the magnitude of torque is literally just the magnitude of the r, or the vector of the radius times the vector of the force. And just like we saw with the area and volume formula, it is the same thing as the magnitude of r times the magnitude of force times sine of whatever your angle is. So depending on what information they gave you, depends on which direction you'd want to find. Okay, so if we have the vectors, we're going to use this because that's easy. If we don't have the vectors, we would do this, but we would need the angle. So let's look at the first example. Anyway. All right, so a bolt is tightened by applying a 40 newtons of force to a 0.25 meter wrench, as shown in figure 5. So we have a 0.25 meter wrench. We're doing 40 meters of 40 newtons of force, and the angle I'm doing it is at 75 degrees. So in this case, I do not have vectors. I have the actual magnitudes of them. So we're going to use this side to find my torque. So my torque, and I'm not making the funny looking T because it's harder to make than an actual T. So R in this case is 0.25 meters. My force is 40 newtons. And then I have sine of 75 degrees. So we would multiply all those together. Sheet and copy it from the book. So it is 9.66 Newton meters of torque. Okay. One more. All right. So in this one, I have a wrench that's 30 centimeters long, lies along the positive y-axis, and grips a bolt at the origin. A force is applied in the direction of 0, 3, negative 4 at the end of the wrench. Find the magnitude of the force needed to supply 100 Newton meters of torque to the bolt. So in this situation, they give me vectors. Kind of. So they give me the length of R, and then they give me my F direction. But they don't necessarily give me, they don't give me the angle or anything else with it. So what we can do is the first thing we're going to do is we're going to find our angle. So we need two vectors to do that. So I have one vector. the 0, the 3, the -4. I need my other vector. So it says 30 centimeters along the positive y-axis. First off, this is in meters, correct? So I want my units in meters, not centimeters. So, and it's along the y-axis, so I'm just going to put it in the y. So 0, 0.3, and 0. Does that step make sense? And how I did that? So now to find the angle between two vectors, it was the dot product of A and B over the magnitude of A and the magnitude of B. So the magnitudes, so we'll say that's A, that's B, because it doesn't really make a difference which one's which. So the magnitude of B is easy, that's 0.3. The magnitude of A is 5. And then if we did the dot product, remember that's just multiply and add the pieces together. And we get, I think it's 0.9. Because it's just the middle one that actually is going to do it, I think. So now I need to find the arc cosine of that. So 9 over 1.5. And we get the angle is 53.13. So theta equals 53.13. All right. Any questions with what I got there? Okay. Because in essence, what we're looking for, we have, the reason we had to do that is because we have this. 100 equals 0.3 times f of cosine theta, or sine theta. That's what we have. And I'm looking for the f. So I needed theta to find the f. So now I have 100 equals 0.3 times sine of 53.13 f. So I can take it and divide. And get my answer. So I have the 100 divided by the 0.3 sine 53.1. It's approximately 417 newtons of force. So using the cross products, we can now find torque. Huh? That's a lot of force. And then just get the blowtorch. Yeah. All right. This is what happens in math class when it's a math class and a physics class. We just pick some numbers, and sometimes they make sense, sometimes they don't. So if you think about it, like, so we did all this right. If we increased the size of the wrench, does the torque go up, or does the force go up or go down? Right. Yes. So if this, so that when we look at it, if that's higher, the angle changes, which means this all changes too. So it can actually make quite a bit of a difference.
Looks like what, an inch and 20 KML volt, Inconel volt.
All right.